Welcome to Learning to Engineer. Today we will see how a BJT works. This is going to be a very conceptual video. Don't need to take any pens or pencil. You just need to pay attention to what I am going to say. Next video we will solve some problems in this concept. Let's get started. In previous video we saw a PN junction diode which consists of P material and N material of equal widths. Okay, the P material will have the majority carriers as holes, which is called as the spaces, which is just the positively charged particles, and the N material will have majority of electrons. Electrons are negatively charged particles. When both of them have the same area, the chances of whole electron recombination is fairly the same, because there will be like 90% of holes in a P material and there will be 90% of electrons in N material, and fairly the whole electron recombination factor is going to be the same in a PN junction diode. Imagine this scenario. Okay, this is a diode. I'm just giving a very rough example. Okay, in a P material you have 90 holes and here you have 91 electrons. Okay, so fairly both of them will have a same number of quantity, and therefore the depletion region will be even during the reverse bias, or when it is unbiased there will already be a small depletion region, and when you are pumping in holes through this P material, the depletion region will start to break. Then as the electron continues flowing after a certain threshold, then this will be completely moved off and thus conduction happens into this diode. This is how a diode works, right? In the same scenario, consider a place where you have a big area of P material and a very thin area of N material. Okay, you are having a large bar of P material and a thin bar of N material. So now what happens? Say for example 90 holes are present in this material and there will be only one electron, or not even that. This is so thin. In N material the majority carrier is electrons, right? But when you are making the bar so thin that the possibility of whole electron recombination is less, then what will happen? A fairly thinner depletion region will form. I am going to even divide this. What I am going to do? I am going to place another big bar of P material here. Thereby, this one electron will be competing whether to form whole electron recombination with this P material or with this P material. So the competition is more, right? Here you will have 19 holes, here you have 90 holes, but this one electron is only there. So what happens to the depletion region? It will be even more thin compared to what you see in the diode. So this is the difference between a diode and a transistor. The difference lies in the fact that the substrate or this N material in a PNP transistor is very small, that the depletion region is going to be thin, and when you are forward biasing one region and when you are reverse biasing another region, this becomes even more thin and the conduction happens quickly. This is how a BJT works. I explained this with a PNP transistor where P is called as the collector region and N is the base or the substrate, and this P is called as the emitter region or E. This is a common base configuration where the base is common to both collector and emitter power supplies. So this is a common base configuration of transistor. This can also be modeled in another way. We saw PNP, right? Consider a case where you are taking an extra large bar of N material and a small P material and another extra large bar of N material. The competition is same, right? It's just like what you saw in the previous case, but just that there will be more electrons and very less holes available to form a barrier region. Okay, so same when you are forward biasing one set of terminals, and when you are reverse biasing another set of terminals, conduction happens. What if I'm forward biasing both these terminals? This is called a saturation region of operation, and in this region the transistor will be magically transformed into a wire where conduction is so maximum that it is equivalent to replace that transistor via wire. Usually we use a transistor in active region where it operates according to the curve that is present in the data sheet. So it is safer to operate the transistor in active region when you are when you are using transistor in saturation mode. It means that it conducts to the maximum possible extent, which is same as the input current, and this transistor is not generally used in saturation mode. Actually, you will always use it in uh, active region. Okay, so depending on how you are connecting the transistor, what power supply you are going to do to the p and n junction, which a substrate is chosen as a common mode, common base or common emitter or common collector, which configuration you are going to use. All these factors will decide the output and input current and hence the operation of the transistors. If you buy the transistors data sheet, you will understand that in different configuration, the performance of the transistor will be different. I'll explain these curves in my next video, and thanks for watching. If you have any doubts, you can email to learningtoengineer@gmail.com. You can just type that down in the comment section also. Thank you.